Thanks for coming. Welcome to today's seminar. It is a pleasure for me today to welcome an old friend, Alberto Sainz-Dalda. I'm sure that many of you already know him because Alberto, hello. Alberto spent a few years working here at the IAC, although he was never formally an IAC employee. Actually, his affiliation was with TEMIS SL, the society that exploited the TEMIS telescope. And so basically, Alberto worked for TEMIS as a telescope operator, but then in his spare time, he did a very nice PhD thesis on solar astrophysics, studying the decay of active regions under the supervision of Valentin Martinez-Fillet. And then after finishing his thesis, what was it, in 2001?
Nine.
Okay, sorry. In 2009, he got a postdoc position at Stanford University with Lockheed Martin to work basically with the SOHO space mission, specifically the MDI instrument, and the transition to its successor, the Solar Dynamics Observatory, SDO, and more specifically the HMI instrument. Right? Although I think your job was in support of the whole mission in general, not just HMI.
Yeah, more or less.
And then Alberto has been working there ever since, very happily. And I think I'm very happy to see him well established in Stanford and Lockheed Martin. And we've had him here as a visitor for the past 3 weeks. He's been working with some of us, with me in particular. And I think it's a great opportunity to learn a little bit more about flares, which are, as many of you know, very high energy explosive events that take place in the sun. So thanks for coming, and
So thank you for having me here. It's my pleasure to see, again, friends, colleagues, and other people here around. So a couple of weeks ago, Hector told me that a cute, smart girl is going to ask me something. And I'm here. I'm very excited. So thank you for the invitation, for giving this seminar. The point is that, as you know, this is a general public, AC public. So I have to find some interesting topic that most of the people here around could understand, and at the same time don't feel that they are wasting their time, which is important sometimes. So I decide that this topic, flares, is enough interesting because, you know, the space weather and all the implication in the Earth and these things, right? I'm not an expert at all in flare activity, so I decide that go to the very nice, smart guys of NASA and see what they say. So I have this small video that explains very, very well what it is.
Solar flares may seem like faraway events, but they can damage satellites and even ground-based technologies and power grids. Every 11 years, as the sun reaches its maximum activity, they become bigger and more common, and that increases the chances that one will significantly affect Earth. So what are these solar eruptions? A solar flare is basically an explosion on the surface of the sun, ranging from minutes to hours in length. Large flares can release enough energy to power the entire United States for 1 million years. Flares happen when the powerful magnetic fields in and around the sun reconnect. They are usually associated with active regions, often seen as sunspots, where the magnetic fields are strongest. Flares are classified according to their strength. The smallest ones are B class, followed by C, M, and X, the largest. Similar to the Richter scale for earthquakes, each letter represents a 10-fold increase in energy output. So an X is 10 times an M and 100 times a C. Within each letter class, there is a finer scale from 1 to 9. C-class flares are too weak to noticeably affect Earth. M-class flares can cause brief radio blackouts at the poles and minor radiation storms that might endanger astronauts. It's the X-class flares that are the real juggernauts. Although X is the last letter, there are flares more than 10 times the power of an X1, so X-class flares can go higher than 9. The most powerful flare on record was in 2003, during the last solar maximum. It was so powerful that it overloaded the sensors measuring it. They cut out at X17, and the flare was later estimated to be about X45. A powerful X-class flare like that can create long-lasting radiation storms, which can harm satellites, and even give airline passengers flying near the poles small radiation doses. X flares also have the potential to create global transmission problems and worldwide blackouts. The seriousness of an X-class flare pointed at Earth is why NASA and NOAA constantly monitor the Sun. NASA's heliophysics fleet of spacecraft can now see the Sun from every side and in many different wavelengths. This unprecedented coverage is enabling scientists to predict and detect space weather events like flares and CMEs with ever greater accuracy. With advanced warning, governments and companies can take steps to protect their technological infrastructure so that the worst scenarios will never happen.
So, I think now we can have a general idea what we're talking about. And the first thing is to say that the flare is an observational, phenomenological solar future. That's nice because we can identify, taking into account the definition, it's a sudden, rapid, and intense variation in brightness, period. Nothing else. If you see an enhancement of the brightness in the solar surface, this is a flare. The flares can be related with coronal mass ejections, with microjets, with larger duration events in terms of jets too, but this is not a flare. The flare is the enhancement of the brightness. So it's good because we can identify, but it's bad because there are other events related with flares that we have to explain. So apparently, the flares occurs with the magnetic field, so the magnetic energy is building up in the upper layers of the solar atmosphere. Then reconnection occurs, and then all this energy is released. And it's released in many, many different ways. This can be released in thermal energy, in non-thermal energy, in coronal mass ejection, I mean in high particles going out of the sun, in many different ways, okay? So that's very, very interesting to know what is the process of this reconnection and of this final enhancement of the brightness. One of the other interesting things is that the flares can be seen in almost all the all the electromagnetic spectrum. So we can observe in many, many wavelengths, okay? So that's good because we can use several instrumentation to try to understand the flares. So I guess that the intention of this talk is that I explain to you more or less what I have been doing the last years in Stanford and Lockheed. And I thought that this is a very good topic to explain that. And as I mentioned, I'm not an expert at all in flare, so I follow. This is a very nice review. It's by Shibata and Magara, and you can find there a very, very interesting review of this flare activity, the process of flare, all the things, right? We can characterize the flares depending of the kind of associated ejection. As I mentioned, they are related, but all these events, or more of them, they can occur without a flare. So we can have a coronal mass ejection and not a flare, okay? And we can observe a flare, but not a coronal mass ejection, okay? We can also characterize depending on the magnetic field, of the velocity, of the time, this kind of things makes that the flare is very wide target in the solar atmosphere in terms of trying to understand. As I mentioned, they can be they have been observed in giant arcades. In LDE, this is long duration events, can occur during hours, days. And it could be observed in impulsive flares that is very sudden, and other, like in extreme ultraviolet microflares and other things, right? Okay, so here is the model. You can see, first of all, we need a magnetic field, a strong magnetic field, as it was mentioned in the movie, in the photosphere, in the very bottom of the solar atmosphere. And then we have in the upper layers, we have the loops with the magnetic field, and then we have a reconnection. And it's there where the magnetic field is reconnected, where we observe the brightness, the Heisman of the brightness, and this is where is located the flare. Okay. Of course, as I mentioned, there are many different events related with flares. So that means there are many different models. This is one of the first models. It was proposed in 1974. And you can see it's mainly the same thing. You have a magnetic field in the photosphere and crossing the chromosphere. And then you have a reconnection. This is the called X point because it's like an X topology reconnection. And then there is a shock going up and another going down. And sometimes this shock going down, what is going very energetic and fast, create another flare and a propagation of the flare. After the observation with satellites in the 90s, observing the ultraviolet and X-ray, this is soft X-ray observation by a Japanese mission called Yoko. Other models try to fit the observations. So this is a very sophisticated model. The name is something like CKSHM. What is the authors of all the people that contribute with some idea to this model? Basically, you can see is basically the same. You have a reconnection area, and you have a downflow of fast shock and excitation of this part. Okay. Now we have better resolution, and we observe a small two sides loops, and we can observe also excitation in the upper part of the loops. So then there is another proposed model, or we can see this jet associated to the anemone. It's called anemone because the shape of these things reminds to an anemone. And you can see the flare in this part of the topology. There are many observations of these kind of events, especially in the last years, because we have several satellites observing the corona and also the chromosphere. Okay. So what is the investigation that we are doing? I'm working in this topic in collaboration with Lucia Klein. She's working in Lockheed too. The idea is that the magnetic field in the upper layers of the solar atmosphere is driven by the magnetic field in the photosphere. We know that the movement, the relative movement of the foot points of the coronal loops are related with reconnection in the upper layers and can be related with flares. So our investigation is focused on the study of the magnetic field in the photosphere during the flares, during the flare events, right? So that makes that's a little bit challenging because you need to observe simultaneously the photosphere, the upper layers of the sun, where it's easy because there is a lot of satellites right now, so we have this kind of data. But to observe in the photosphere, when a flare is occurring, especially in a ground-based telescope, is very, very challenging. You have to be very lucky. So before to go to our investigation, I'm going to explain some very basic concept. I'm sorry, guys. It's interesting the people distribution in this room. So I sorry. I apologize to this part of the of the room, because many of these people are really expert in the topics that I'm going to talk right now. So maybe it's boring for you. You can WhatsApp, check, Facebook. You can even read a paper. It's very interesting too. Anyway, so I'm going to talk about the small ingredients that I consider that we have to keep in mind or refresh in our mind. First of all, it's about polarimetry. We know that the vector electric field is rotating in a plane perpendicular to the direction of its propagation. So that means that in the general case, it's describing a kind of ellipse. So now what I want to do is just only characterize this ellipse. It's just only a geometrical problem. I want to find some parameters to describe if this ellipse degenerates in a perfect circle or can degenerate in a very straight line in this direction or in another direction. So we can characterize this geometry with 4 parameters. And we call these parameters Stokes parameters. As you can see, this is the projection of the vector electric field in the orthogonal planes in X and Y. And these parameters, I, Q, U, and V, describe exactly this ellipse. And you can see this is an average, because we are talking about a quasi-monochromatic electromagnetic plane wave. So it's a mathematical, if you want, idealization, right? And another interesting thing is this. As you can see, here is the amplitude of these waves, of the projection. So with these parameters, we can completely characterize how is this ellipse. The question is why? Why I want to know if this ellipse is a circle or a line, or why? Well, because we need to know this to understand what is happening in the sun. And we need to measure. If we use just this very simple experiment in our optical bench, it's a linear retarder with a phase, a delay phase, characterized by a delay phase, and a linear polarizer, where is characterized by an angle of the direction where the light can go through. The intensity that we measure in the CCD is given by this. So we have an intensity measurement. It's intensity measurement. What we measure in the CCD in our detector is amplitude, is intensity. We are not measuring Stokes parameters. We are measuring a combination of intensities with a parameter. Okay? So if we want to recover the parameters, we have to do a combination of this linear retarder and this linear polarizer to get the parameters. Okay? So again, why are we interested in the Stokes parameters? Well, the question is why the light is polarized. It's polarized. So there are several mechanisms that polarize the light. There is the Zeeman effect, the Handler effect, the scattering polarization, the atomic anisotropy, and these kind of things, right? In this talk, we are use only the so-called Zeeman effect. The Zeeman effect is just only the splitting of the spectral lines in presence of a magnetic field. In this case, the system is degenerate, and you have sub-levels that you have to take into account. Okay? So what you finally have is you can measure the intensity coming from the sun, and you can put this system, the linear polarizer and the linear retarder, and make this combination, right? And when you get is intensity measurements. And this inside of these intensity measurements, there are the Stokes parameters. How do you do? You can subtract these two spectral lines that have been observed with this system, and you recover this. This is what we call a Stokes B profile, where it is just only a spectral representation of the intensity of the signal related with the B parameter. Why is important that? Okay, because we know, because of the Zeeman effect, that this, the presence of a magnetic field in the solar atmosphere create this apolarized light. So if we want to know how is the magnetic field in the solar surface, we just need to know how are the Stokes profiles, how are the Stokes parameters that characterize this light. Okay. So, for example, this is two images taken in circular polarization and the other in linear polarization, what we call V and Q, because these are the parameters that characterize the leaves in this way. This circular polarization is giving us information about the line of sight component of the vector magnetic field, while the Q and the other parameter U are giving us information about the transverse component of the vector magnetic field. So you can get this kind of image. This is a full day's image of the sun observed in a Stokes V, in circular polarization. So then, this is an image of the line of sight component of the vector magnetic field, where black means, in this case, going inside the screen, and white going out the screen. But this is just only the line of sight component of the vector magnetic field. So, what about the spectropolarimetry or polarimetry and flares? The point is that we, as I mentioned before, we want to know how is the magnetic field in the photosphere to understand what is happening in the chromosphere. So then we have to understand the polarimetry, the polarimetric data that we are taking. We know that in flares we have huge intensity gradients, as you can imagine, because it's a sudden, intense enhancement of the brightness. So we can expect crazy things in the intensity. And the point is that, as I mentioned, we are subtracting intensities to get Q, U, and V. So if the intensity images that you are measured are very weird, you can expect very weird Q, U, and V most of the times. In addition, you are subtracting two things, so they have to be perfectly aligned. If you have a disalignment, you have spurious signals, and of course you are getting a wrong output. So that makes the ground-based observation very, as I mentioned, very challenging, because we have limited observing time, and usually when you are observing, you know, there are clouds, the scene is not good, everything is happening. So then you can go to the space, because in the space there are not clouds, everything is working, and these people are really smart, and they do amazing telescope and put that up, right? So then now I'm gonna explain the three instruments I have been working on. I have been working with Hinode. Hinode is a Japanese mission, and it has several instruments, and it has a solar optical telescope where it has three different instruments. One of these is a spectropolarimeter. So here is the spatial resolution, the spectral resolution. What is the point? This spectrograph has been designed to observe photospheric lines, iron 6301, 6302, where are very well known. We know very well the behavior of these lines, and we can interpret very well the polarimetry data from this line. The point is that in this case, you have these amazing pictures without clouds, with constant scene, because there is not. It's very nice, right? And you can observe during many, many hours, not only during the day, right? But the point is that, of course, you are making a scan, you are scanning with your slit spectrograph on the solar surface, and it takes time. So, for example, for this region, for this sunspot, maybe this is something about 30 minutes to have all these images. Because what you are getting, in fact, is this kind of data. This is the slit of the spectrograph, and when you get is intensity images like that, like this one, and then subtracting them, you get the Q, U, and V Stokes parameter. Now, if you make a cut in the spectral direction, this is the spatial direction, this is the spectral direction, then you get the Stokes profiles. As you can see, they have a very particular shape. The intensity is in absorption, so you have these valleys. This is 6301, this is 6302. In Q and U, you have this symmetric profile with respect to the core of the line. But in B, it's antisymmetric. Okay? So this is very nice profiles, very nice, everything is beautiful, the signal is great, but of course, it's not like that every time. Sometimes we observe that these profiles, especially in B profile, there is asymmetries. That means that either the intensity of one of the lobes is very different to the other, or the area is very different to the other. It can happen also in Q and U. It happens. What does it mean? Well, when we have these asymmetries in the profiles, we know that they are produced because there are a gradient either in the vector magnetic field, that's in the strength, inclination, and azimuth, or in the velocity line of sight. If you have a gradient in one of these parameters, you have an asymmetry in the Stokes profiles. Many people here has been studying these profiles for many years in sunspot, in active regions, and other things, and we know that in the penumbra, for example, there is a lot of asymmetries in the Stokes profile. This is what we call net circular polarization. If you make an integration about this line, okay, if you make an integration and the profile is perfectly symmetric, the integration is 0. That means that it's absolutely symmetric. Well, when we do that on penumbra, we know, you can see that the net circular polarization is almost different to 0 everywhere. So we have different gradients, a lot, sometimes very strange, sometimes not so strange, but it's very, very challenging to find a place where the net circular polarization is equally, perfectly equal to 0. Okay, so now we have the Stokes profile, but how can we get the information? How can we recover the information from the Stokes profile to the magnetic field and the velocity that we need? Well, there are several methods. This is the inversion method. And there are other methods that they are straightforward. They are slightly different. But every method needs one thing. It's a solar atmosphere model. Depending on the model that you consider, you can get different output. If you are considering a very basic model, what you get is a very basic output. If you are considering a more complex model, taking into account more physics of the atmosphere, then you can get more realistic output, and then you can fit better. What we are doing is, okay, we have the model, we are resolving the radiative transfer equation with the Ranskovsky solution, and then doing that, we can get the profiles, the Stokes profiles. We have for an atmosphere model Stokes profiles, and I have my observations. So now what I have to do is to compare and try to fit. We try to fit with a least square minimization method, okay? And if it is very far of the model, then you change slightly the model and do an iterative method, okay? The more basic atmosphere model is the Milne-Eddington atmosphere. In the Milne-Eddington atmosphere, we consider that there is no variation of the parameters that characterize the atmospheres. So that means that all are constant through the line of sight. in addition, the source function varies linearly with the optical depth. Okay. What does it mean? That one of the things that this atmosphere has is that the Stokes profile, they are perfectly symmetric because it's taking into account a static magnetic field. It's constant through the atmosphere. So you can only get symmetric profiles, or antisymmetric in the case of Stokes V. So with this atmosphere, you cannot fit asymmetric profiles because the model cannot do it. So you can go to a more sophisticated atmosphere, and then we use the LTE, the local thermodynamic equilibrium assumption. We consider that our atmosphere is in local thermodynamic equilibrium, and in this case, the atomic population are easily calculated through the Saha-Boltzmann equation, and the source function is the Planck function, depending only on the temperature. Okay? So in this case, you can reproduce asymmetries. Okay? There are several methods again, and here there is really expert on this topic. So it's a little bit more sophisticated, but is working very well in the photospheric weak lines. Okay. So now I'm going to talk about other instruments that we are using. As I mentioned, we can observe the flares in the upper layers. So we are using this instrument, where is the atmospheric imaging assembly. It's on board of the Solar Dynamics Observatory. It was launched in 2012? No, sorry, 10. And, American people, you can put a telescope, they're up. Why? If you can put 4. So they put 4 telescopes, they're up. 1, 2, 3, okay? Each of these telescopes has a 20 centimeters primary focus, and it can observe 8 wavelengths. It's not wavelength, it's spectral range, okay? In 10, 12 seconds, each of these range. So it's amazing. You are observing in 8 spectral range, in 8 solar atmosphere layers simultaneously, with a very good spatial resolution and constantly. So this is the thing that you get. As I mentioned, you have 4 telescopes, and you have half of the primary mirror is observing, has a coating and observing a spectral range, and the other half is observing the other. And then there is a wheel filter in the primary focus. So you have all these lines. Most of them, they are ions, and this is the, what is my mouse here? This is the response, and here is the temperature that they are observing. As you can see, there is a range. They are not observing at 1.0 million of kelvins. No, it's a range. So you are observing several layers of the atmosphere simultaneously. Okay, transition region, flaring corona. As you can see here is clearly the flare, this enhancement of the brightness, and you can observe in different layers, in the corona, in the lower corona, even in the chromosphere. And in addition to this assembly of telescope in SDO, there is this HMI. As you can see, that's remind us to the magnetogram that we were observing before. The point is that they put this together. I'm going to show you one thing that you can observe with AIA. As you can see here, what we have is a filament. A filament is a cooler. A filament is filled by cooler plasma than the environment. It can be several thousand cooler than the rest of the environment, so you see as dark. And as you see, after the release, you can see here the propagation of the flares. As you can see, this movie was observed just 1 month ago in September. Right now, it's extremely easy to get flares in the sun because we are close to the maximum. So that means that there is a lot of active regions, and as I mentioned at the beginning, the flares are related with the active region topology. Of course, we are in California, we are very cool, we do amazing things, so we can do something so crazy like that. I guess you have realized I'm not very serious guy, but these guys are very, very serious. They are. I'm not, but they are really serious and smart. Very smart guys. Yeah, absolutely. Okay, so this movie was done by Untitled. He's the big boss in Lockheed Martin laboratory, solar laboratory. And as you can see, is this. It's a little bit psychedelic, but you know, we are from California, so we can do that. What we are observing here is the Rand's difference. This is what they call global flare activity. What they are trying to tell us with this colorful, amazing, crazy movie is that the flare activity can involve all the global magnetic field. Sometimes it's not so evident. Sometimes it's really, really evident. Let me show you one of these really evident. For example, I think one of these, maybe this. This is nice. Okay, so you can see there all the propagation. This is the combination of 3 spectral range images, and this is what we call a Rand difference. That means that we are subtracting one image to the previous one. But in this case, they are using logarithmic scale. They are subtracting the logarithm of the image for one spectral range, and they are subtracting to the previous logarithm of this same. And then they are relating any of these Rand difference to a color. Okay? So you can see this really expanding. Just they are occupying most of the solar surface, and sometimes you can even observe that when this shock is arriving to other active regions, the shock is activating the other active regions. Okay, so let me maybe show you. There is one crazy. This is very long movie, so it's something like 30 minutes or something like that. This is a combination of these flares during the full mission of AIA. Yes, crazy people, but very serious and smart. Huh? No, really, really. You can see there propagating. It's lovely, but I don't know. I think they were, I don't know. Okay, so as I explained, what they are doing is this, okay? And they are associating any of these spectral ranges to one color, and this is because you have so colorful movie. Okay, as I mentioned, in this, on board on this satellite, we have the HMI, okay? And the HMI is the helioseismic magnetic imager, and what this instrument is doing is scanning with to enable Lyot filter. It's scanning one iron line, 6173. This is also a photospheric line, and it's scanning in 6 different points. So what you have here is just only 6 points. Okay, it's like a spectrograph, but with extremely low spectral resolution. But even with 6 points, you can recover the magnetic field. And in this case, what they are using in HMI is a Milne-Eddington assumption. That is done because it's very fast, and you don't have so much information, right? You have only 6 points. 4 times, because you have IQ and B, but you cannot fit very well the things. So one of the reasons because I'm here is because I'm trying to challenge this observation, and I'm trying to do an LT inversion with this data. Okay, so Basilio Ruiz, he's a real expert. He's the master of the universe, of this universe. Okay, He's helping me to do that, right? To recover the magnetic field with gradients from HMI observations. Why is it so important to have this variation through the atmosphere? Well, because there are some quantities that needs a very accurate measurement of VC, of the line of sight of the vertical component of the magnetic field. Okay. What you can do with these images, as I mentioned, is a full disk. We have every 45 seconds, we have a magnetogram, a line of sight. But in addition, every 135 seconds, we have all the Stokes parameters. And what we are doing is making inversion every 12 minutes to make an average. We can do with a shorter time, but we are using 12 minutes average for making the inversions, okay, to get a better signal-to-noise ratio. So the things that you can get here is a magnetogram. In this case, the polarities are represented by blue and red. So blue is positive, red is negative, or maybe it's reversed, but who cares about that right now? And this is what you can observe. We can observe for every single point, we can get the vector magnetic field. That means we can get the vector, the magnetic field strength, the orientation. We can determine in every single point, every 12 minutes in the sun constantly. This is one thing that, unfortunately, we cannot do from ground-based telescope. Not with this, in this long time. This is 5 days, okay? And it's really, really amazing. It's true that the spatial resolution is worse than Swedish Tower here or in Big Bear in California and many other telescopes. But we have a long periods of vector magnetic field data. As I mentioned, we need to know how is the vector magnetic field in the photosphere. But with this, we can do that. We can do extrapolations using several approximations, and you can determine how is the magnetic field configuration in the upper layers from the magnetic field in the photosphere. Okay? So these movies were done by my colleagues in Stanford. And of course, as I mentioned, we have a very high temporal cadence, and we have a constant observation. So you can do the temporal evolution of these loops. And then you can compare with the observation that AIA is observing simultaneously in the same observatory in SDO. Okay? Okay. So finally, we are using ground-based telescope because, of course, you cannot get everything from the space. We would like, but we cannot, fortunately, also. So we have some observation from IBIS. IBIS is an Italian instrument in DST, in the Dance Solar Telescope in Sac Peak, where our lovely Valentin is living right now. It seems it's an amazing place. And this is a Fabry period. So what you are doing is taking images in different points sequentially, in different points of an spectral line. So you have, for every of this point of this spectral line, you have an image what is taking very fast. And you can go, oops, you can observe, oops, yep, you can observe one line and then the other one. And if you go to a spatial position and take, for this point, the values of the intensity of the different line, of the different image, you have a spectral line. Okay? Okay. So this is what we have. Of course, you know, we have sometimes bad scenes, sometimes good scenes, and if you have good scenes, you can take post-observation techniques to improve the signal, right? The spatial image. Okay, we have this observation. Lucia was observing this an active region is in this date, and she catched a flare during the observation of the sunspot. So she was observing a sunspot, and fortunately, there was a flare in this sunspot when she was observing. She was observing in the photospheric line, 6302, and in the chromospheric line, 8542. So this is the kind of data she got. And as you can see, she was observing two different sunspots. Here, you can see this filamentary structure is like this is a kind of penumbra in this maybe dissolving sunspot. And you can see here, where is my mouse? Why disappears? Okay, here. You can see this structure here, okay? And you can see also here this brightness here in, this is chromospheric image, this is photospheric image, okay? Okay, so she also look at the AIA data and she observed this. These loops are going exactly to this place in the sunspot, okay? So then, and in this case, you can see an outward motion in the outer part of this kind of filament, but here apparently it's going inside. So, yes, okay. If you look at the Stokes profiles, you can see here this is a kind of magnetogram. This is an Stokes big image. And you can see here the polarity of the sunspot is black. And you can see this structure opposite polarity. As you can see here, the profiles, how is one is reversed with respect to the other. What's happening? This is in the photosphere. What's happening in the chromosphere? Where? Well, in the chromosphere, she's observing it's mainly the same, but with the same polarity. It has apparently the same polarity here, but it is a brightness in this, exactly in this point. Okay, so she knows because she was observing the flare activity that in these active regions happen a flare. So she proposed this kind of configuration, very basic configuration. You have the sunspot, you have the umbra, you have the penumbra with more inclined topology, inclined magnetic fields, and there is an inward who is making a reconnection in this area. Okay, just one case. It's just one observation. So, okay, so then we observe other. This is a movie showing this active region. Please pay attention just only to this image and this. This is the HMI continuum image, and this is the magnetogram. And as you can see here, you can see now opposite polarities filaments going inside of the umbra. You can see one there, other here. Okay, this is the magnetogram. Okay, opposite polarities going here. If you look at again here, you can see how this filament is going inside of the umbra. It's broken the umbra, but they are not becoming a light bridge. Okay, a light bridge is a large structure who is breaking the penumbra. Okay, usually showing convection patterns inside. That's not the case. In addition, we have also AIA images, and we have the GOES. GOES is giving us the information of the X-ray flag, so it's giving us any of these peaks is a flare. Okay, so we are sure that a flare happens during this, the temporal evolution of this sunspot. Fortunately, we got some data from EVIS too, and this is the images. You can see this kind of tongues, or we call unusual umbral filaments. They are going inside, they are rolling, but they are keeping there for hours, days, okay? They are slightly larger than penumbral filaments. As I mentioned, we cannot observe with this spatial resolution convection patterns like in light bridge. So what we study is what is happening in these filaments in the photosphere and the chromosphere, and we have exactly the same behavior. We have a brightness in the chromosphere images, okay? Here is the time when the flares occurs. So as you can see, these areas, they are excited before and after the flares. But this is in the chromosphere. The flares usually is happening in upper layers. Here we have also, this is the image, but in the near of the core. So this is very chromospheric image, and you have all this enhancement of this, and you can see them here, okay, and here. The flare again is in this middle point. Okay, so this is the red wing, and one thing you can distinguish perfectly the same unusual filament that we're observing in the umbra. but in a little higher layer. So again, we compare with AIA images, and we see that in this exactly the points where these usual filaments are going to the umbra, we have these loops that they are going outside of the sunspot. And we see that there is a flare here. Where is my mouse? Here again? Okay, here. So now we go to Hinode, and there is data from 6302, spectroperimetric data. So then we use an LTE code that allows us to get the magnetic field and thermodynamic parameters with variation through the atmosphere. So we use these inversion methods. We feed the profiles with the output of our model atmosphere, and we can recover the magnetic field and the thermodynamics parameters. As you can see, there are crazy, absolutely crazy Stokes profile. There is 3 lobes, Stokes B, so you cannot fit with a Milne-Eddington. That's not really true. This is the data that they are systematically offered by HMI and Hinode. They are doing inversion automatically with a Milne-Eddington. As you can see here, you can see this blue area. This is velocity. This is a Doppelgram after the Milne-Eddington inversion. As you can see, this is opposite velocity than this. Where's my mouse? Here. Okay, that this one. As you can see, we have half of the sunspot is red and half of the sunspot is blue. This is the so-called Everset flow. There is an horizontal outward flow in the sunspot. When you are observing in a projected location, this is going out and this is going to you. So this is red shift and this is blue shift. Okay? But you can see here that this is clearly blue in the red shift area. So that means that this is an inflow from the outer part of the penumbra to the inner part of the umbra. And this is just only a Milne-Eddington inversion done with HMI and with Hinode. But we are very nice, very cool, and we want to feed these crazy asymmetric profiles. And then you can get this. You can get mainly the same, but with more accurate values. So Milne-Eddington is working, okay, good. It's like fast food. You can eat some fast food. It's very fast. But if you want hot-made food, you have to go and work a little bit. And then you can enjoy a really good food. Okay. So then we do that. And in our case, we do an inversion taking into account 2 components. We say, oh, no, the magnetic field is going to have 2 components in the atmosphere. The atmosphere is going to have 2 components. One is more horizontal and the other is a little bit inclined. And then you get information of these 2 components, okay? As you can see, this is the most horizontal component, and you can see this absolutely opposite inflow. And here you can see blue and slightly here red. This is the foot point. So what you have is a kind of filament going out from outside to the inside. Again, in these places we know a flare occurred. So this is because we are very interested in what is happening there. Okay? So we have several scans done by Hinode, and we do this inversion, and this is always keeping all the time. This is, as you can see, starting in September 23rd, and it's finishing 3 days later. And it's always keeping this inflow. So what we propose is this this model, okay? Is what we call sheet model, because we can understand that this umbral filament, this inflow is coming from a kind of sheet that is going from the photosphere to the chromosphere, because we are observing simultaneously in the photosphere and in the chromosphere. And in addition, you need some free to roll this area. The other option is that you have a massive umbral filament. That means that you have enough high density in the filament that you are not observing, in fact, in the photosphere. The log tau, the optical depth that you are observing, because it's so dense, is a little bit higher. Okay? So this is what we are working on, understanding the topology of the magnetic field in the photosphere to understand what is happening in the chromosphere with all these tools. One thing is that I mentioned we observe this in iron and in chromosphere. Why are not inverting chromosphere? It is the other reason because I'm here. Because to invert data in spectropolarimetric data in the chromosphere is a little bit more challenging because the chromosphere is very dynamic atmosphere. So you cannot, in most of the case, well, depending on the line, you cannot make a LTE assumption. You have to go to a little bit more sophisticated case, what is non-LTE. Okay, in this case, the population of the atomic level, they are calculating, taking into account the statistic equilibrium, and you have to be careful what we are doing. Okay, so Hector is an expert on this kind of codes. He develops a very successful code, and I'm working on these inversions. So that's all. Thank you.
Thanks a lot for this nice talk. Now we have some time, a little bit of time for questions. Any questions?
So when you talk about this filament going into your umbra that has the opposite polarity in the magnetogram, so I mean you weren't very explicit about this. Are you suggesting that it actually has the opposite magnetic polarity?
Yes, we are thinking so. We are honestly not very sure, but in the photospheric lines, we would say yes.
I think we need to talk about that.
Outside, we talk outside.
Just a curiosity. You say that then when there is a flare, there is an increase of emission at all wavelengths. But over this continuum emission, can you see increased emission on some spectral lines? In particular, I'm interested in calcium.
If we can observe...
So is the increase in emission, it's at all wavelengths, right?
Yeah.
But is it more pronounced at some spectral lines?
Yes, this is... if you go here... What is that? For example, if you go here, and you can check this, as you can see, for any of these spectral range, we think we can observe this kind of target. For example, flaring corona, that means that we can observe flares in the corona, right? Or active region, that we can observe the magnetic field in the active regions. And look at here, this is chromospheric, this is 304 chromospheric transition region. So we don't think it's very useful for flare. But the movie that I saw is 304. Oops. And as you can see all these chromospheric features, and you're going to observe also the flare. So yes, you can, for sure, you can observe in these lines. Yes.
Will I see intensity of spectral lines, or will I see a flat spectrum?
I don't understand the question.
Yes, if I had the spectrograph looking at the flare, and I see the spectrum of a flare, will it have
emission?
spectral
Oh
lines?
yes, emission in the core and these things. Yes, of course.
In spectral lines?
Sorry? Yeah. Yeah. Full line.
And emission, yes.
Yeah.
Pure emission.
Yeah.
So I would see things like calcium and sodium and these things.
Yeah.
Okay.
Definitely. Yeah. Sorry, I didn't understand well. Yeah.
I have a question also. you know, there's all this experiment going on since a long time on the pyramid in Teide, looking at this helioseismology. Now with all these new instruments, do you think that this is still worth continuing, or
of course.
What is your opinion on this?
Well, HMI, the images that I saw of the magnetogram in full disk, in fact, this instrument is doing elusive. Okay, so it's doing this exactly the same kind of, let's say, the same kind of observation that the pyramid here. Yes, because the magnetic field is coming from the very bottom of the solar not atmosphere, but from the convection. So we have to care about this. Yes, definitely. And I mean, I can tell you guys, besides, that apparently I have permit to show you some data from IRIS. So IRIS was launched 3 months ago and is observing the transition region. Because in the transition region is very, very, very challenging to understand what the hell is happening there. Okay? And it was just launched after 3 months ago. And these data, they are really, really new. I mean, this is, we have a spectrograph, and we have all this emission that you mentioned in these lines is every time. Every time there is a bright things there, you can see emission in the core of the lines and the whole lines too. Okay? So, yes, of course. The point is that we need more instrument, but the point is that this instrument, they are doing a huge amount of data. We don't have enough time, enough people to look at all this data. But you are very welcome to solar physics if you want.
So, I mean, you have a point there, a very good point, that with these space observatories, some of the ground-based instruments are, you could think that they're getting obsolete because these space observatories can do a better job. But the point is that the instruments like those in the pyramid have been running for 30 years. And these missions, I don't know, they have nominal times of 5 years, 10 years. So the ground-based will give you continuity in the measurements that you have. It will give you cross-calibrations between observatories. And also for helioseismology, for global helioseismology, sometimes you need very long time sets to really look at questions like variability with solar cycles and things like that. So having something that has been running for 3 decades is very, very useful. So they are still useful, I think.
On the other hand, they give you freedom. I mean, you can go up to the observatory and change the experiment, the lines you are observing. That's something that you cannot do. You know, when you are observing with a satellite, you have this, and that's what you have. But I totally agree with Hector, but I have to mention that NDI has been working almost 20 years. Come on, sorry? Yeah.
We cannot give for granted that we will have all the time space missions. It is true that lately there has been all the time some mission looking at the sun. But this is something that may not happen at some moment.
Yeah.
So from the ground you can do things. From space you may do them or not.
Yeah, totally agree.
Okay, if there are no more questions, we invite you to join us for the scientific coffee in the library. And thank you for coming, and let's thank our speaker once more.